example 1 and example 2. In the sense that example 1 we have a whole field, so a solid field. Here we have a gas field. So now keep in mind, usually if you have solid, usually you are given mass analysis. If you have gas, you are usually given volume analysis, which is this case. Okay, so now if you have liquid, this one I cannot say for sure lah, but mostly it's still volume analysis, but liquid can be both ways. But yeah, because it makes sense because when you measure solid, mostly you are measuring the mass. If you are measuring the gas, mostly you are getting the volume. So in this case, this is the volume analysis. So which means you don't really need to do much for this question. You just need to assume 1 kilomole of gas. Then this is just the respective YI. Okay, so you can use the percentage directly. So unlike example 1 where you need to convert, this one you don't need. Alright, so number 1 asks for the stoichiometric air field ratio by volume. So always remember this. If you are asked to find stoichiometric, even and you are not asked to find, let's say you are not sure what to do, you can always find first. It's useful somewhat. So if you need to find stoichiometric, anything stoichiometric, you always assume complete combustion. Because otherwise you cannot solve anything. So by assuming complete combustion, it means that C will get converted to CO2, H will get converted to H2O, N is just N2 is just N2, S will be SO2. But yeah, no, I mean these are the common things that you need to pay attention to for complete combustion, nothing else. Okay, so let's see how we construct this equation. Okay, so generally, so same thing. So all of this, so we put down the entire gas here. So just now, so all these are the 1 kilomole of the supply gas plus the amount of air. So this is air. So how much was the actual amount? What's the theoretical amount? We don't know. So we need to find that. And as you can see, the outlet is just CO2, H2O, and N2 because those are the only things that we have. So here you need to balance them in order for you to find what is A, B, E, C. So the variable doesn't matter, whatever you want to do. Sometimes we put as Y there, sometimes we C here. Okay, so this will be the answer. So C, first off, you look at C. So on the right we have 1A. So on the left we have 0.2, 0.18, then 0.02 but you need to times 4 because it's C4. Then H, same thing, you just go through each of them. So here we say H, right? So 0.2 multiplied by 4. So if you use H2 here, then you times 2 lah. So that's just the.
So where is D?
Where is what? D.
C.
Okay, so 2B, so here 4, 0.2, so 2, 0.494, then 8, 0.02, no other H, then so on and so forth lah. So you do the same for O as well, then you can do for N. So from here, you will be able to get all the ABC. Okay, so once you have found all these values, right, then you can find the stoichiometric air field ratio. So now, actually by default, if you are dealing with gas, air field ratio, again, we will look for an in terms of volume, not mass, because we don't really know what's the mass of the gas. But like in this case, so you can see the question, the air field ratio, we want you to find in terms of volume, right? In terms of volume also means that we are looking for this in terms of mole. the stoichiometric entry ratio is actually very easy. Why? Because it is simply this. So this is the amount of A. So the amount of A is 0.58853. So this is this value. The usual 4.76. You don't need to multiply 29 because we are looking for this in terms of mole. Then at the bottom, actually just divide by 1 kilomole of fuel because you assume 1 kilomole of gas, right? So that's why you don't even need to do anything. So it's pretty much just the ATH multiplied by 4.76. There you get the answer. Make sense? You want to understand this? So if you do entry ratio by mass, you need to multiply by volume. By volume, you don't need to because you're just looking for it. So this one is quite easy. Divide by what? So if you assume 100 kilomole here, then you have to divide by 100. I assume 1 kilomole, so I don't need to do anything, I just divide by 1.
Sir, may I know what is the 2.9 that will be times or not? Huh? 29. What is it?
Molar mass.
Molar mass of which element?
A.
A. Okay.
So that 29, if you look back at example 1, so you can see in example 1, when we look for entry ratio, it's the same thing. So we use the ATH, multiply by 4.76, but we multiply by 29 because we are looking for the mass of the field. In the example 2, we are looking for the mole of the field. So for mole, then you don't need to multiply the 29. Then the 4.76 is by default. So by default, the air will have 4.76 mole. So this is the whole air. So is everyone clear here? Any other questions? If no, then I will go to the next slide. So next slide, actually not much difference from example 1. Is I still present it. Okay, sorry. There is a difference. Okay, let's look at second question. Okay, so the second question asks for the wet and dry analysis of the product of combustion if the actual mixture is 20% weak. Okay. First thing, exam I won't ask for both wet and dry because a lot of work. So most likely I will just ask for the wet if it's not. But here, of course, it's just example and practice, so I ask for both. Okay, so the real question here is this. What do we mean? What do I mean by actual mixture is 20% weak? Remember, we talked about weak mixture and also a strong mixture. So a weak mixture would mean that
less fuel.
Less fuel.
More air.
More air, yes. More air, not less fuel, because here fuel is still point here more, we will reduce it more air. Okay, so which means that if it is weak, this is excess air. Okay, so excess air, 20% weak, again, this is excess air. So the actual air fuel ratio here will be, so since we have 20% excess air, so you just multiply by 1.2 for the air fuel ratio, then you get the new air fuel ratio. So the total number of mole of air will be this. So remember I showed you example 1. So if you have excess air, pretty much if you assume complete combustion, then this 0.2 is actually just the extra air. So you use the so this is the actual amount of air. If I write it like this. So here, this 1.0236 is the actual amount of air. 0.853 is the stoichiometric amount. Or the theoretical amount. So if you minus, then this is the excess air that you have. Then nitrogen, we just write 3.76 times 1.0236 plus. So the nitrogen is just follow back the previous equation, but now 3.76 times the new actual amount of air. So this one I didn't construct the new equation because it's a bit tedious. But basically, if you are to construct the new chemical equation, right? The product, what you get is just same thing, CO2H2O plus O2 plus N2. So CO2 and H2O will be the same as A and B from the previous question because it was complete combustion from the start. So there is no reason for this number to change. The only thing that changes now for O2, this will be the excess oxygen. Then N2 also you will get a new number. So for N2 will be 3.911. So these two are the new values. Actual amount. Okay. So CO2 and H2O will still be the same value. So if you got excess air, actually it's quite easy to construct a new equation, provided you have complete combustion. Okay, so then once again, if you are to find the wet and dry analysis, you list down the number of mole. So you get all the number of mole of the product. So the product indicates CO2, H2O, O2, and N2. Then wet analysis, you make use of everything. Then dry analysis, you ignore the H2O. So this will be the same as example 1. So just for you to practice. So example 3 is also similar type of question, so I think you are basic of it, so let's do it together. So now, so ethyl alcohol, so this will be liquid. So you can see our first example was solid, second example was gas. So now we get the liquid fuel instead. Alright, so this liquid fuel, here you don't need to worry about anything because there is no breakdown on this. We only have one hydrocarbon fuel, which is ethyl alcohol, C2H6O. It's burned in a petrol engine. So calculate once again, we need to calculate stoichiometric ratio. If the question doesn't say anything and it is liquid or solid, then it's always by mass. Okay. Usually only for gas we will do by volume. Then so 2 and 3 actually is still the same question as the previous one. You need to find every ratio but at different mixture strength. So here you are introduced to a new term. For some weird reason, when we are dealing with all this, there are actually a lot of different terms. So I'm just showing you new terms. So here I tell you that mixture strength is actually stoichiometric amount of air over actual amount of air. So it means that this is the inverse of theoretical air. Anyway, was it the theoretical air? What did I call that? What was the thing I used? Percentage amount of air. Percentage theoretical air. Percentage theoretical air. I don't know why they have all these symbols of each other. But yeah, usually so because for this one, we say that this is the actual over the theoretical. So mixture strength is just the other way around. I rarely use mixture strength for exam. It's just that sometimes the question that I got is based on this, so I'll just show based on that. That's all. But again, it's actually simply just the other way around. Okay, which also means that then now 90% will be the excess, okay, for 120% is actually the deficiency of it. Yeah, because it's the other way around. Okay, but never mind. So this one we can do together, like I said, but this is also an easy one. So once again, you just assume 1 kilomole of the gas. So let's again, we assume 1 kilomole of fuel. So complete combustion. Because we want to find the stoichiometric amount. So this one's simple. You have C2H6O, so you just balance this C-O and N2. Then stoichiometric amount, every ratio by mass. So it's just 3 multiplied by 4.76, then 429. So this is always the default value, okay? Then this will be based on the field. So the field will have 2C6H, then 1 mole.
Why need to divide? The previous answer also need to divide. The example 2.
Example 2 divide by 1.
Then why this one cannot divide by 1?
What is FU ratio?
A over few.
So the previous one, what was the mole of the field?
We assume what? Assume. And this one also 1 kilomole.
But we are looking for mass here. So there is this difference. FU ratio generally is by mass. We only do by mole for gas. Because you don't really measure gas by mass, you measure gas by mole. Okay, so now we go to the next question. So the next one is mixture strength of 90 per second. Okay, so again, just now we see the mixture strength is theoretical over actual. Right? So, which means now we want to find the actual air-fuel ratio based on this. So the actual one will be, so previously we found the answer was 9 for the theoretical one. So then 9 divided by 0.9, so the new air-fuel ratio here is 10 over 1. Which also means this is excess air lah. So like I said, so this is excess. So from here we do the same thing as the previous slide. You can find the mole of the air based on this air fuel ratio. Then you can also find out what is the excess oxygen in this case and the excess nitrogen. Sorry, not excess, the actual amount of nitrogen. Because the actual air fuel ratio is more than the. So this mixture strength, that's why I don't really use it much because it's a bit confusing. But since the example use that term, I can just use it to show you what. Okay, then I will move to the next one. Okay, so now you count all these, then we do the same thing again. You make a table, then you find what is the wet analysis, dry analysis. So here nothing special, so just letting you can practice on your own, just check the answer, see whether it's the same once when you are practicing. So just remember one thing when you are doing this wet and dry analysis, you also know that you guys are very prone to have a lot of calculation mistake, right? Yes. So once you calculate it, just make sure that you total them out and check whether you get 100% or not. You get 100%, then it's very likely you didn't make any mistake, unless you mistaken between the dry and the wet, then the one you can have it. So if that's correct, then yeah, you get 100, most likely everything is correct. Okay, so now we jump to mixture strength of 120%. So if 90% is excess, this means still means that this you have deficiency of that. You can see that here the FE ratio is lower than the theoretical one. So from here the mole of the air is 2.5. Okay, so now for lack of air or deficiency of air, right, most of the time the question is supposed to give you the output. Otherwise, it will be hard for you to analyze. But if the question doesn't give you, the only way that we solve is usually we will assume that only CO is not completely burnt. So if only CO is not completely burnt, then output will be CO2 and CO. Because actually water can also not completely burn, then you get voltage also. But this is the typical practice like if you are not given the output. But usually I don't like this, so I don't fancy so much of this because right, most likely the answer that you get here, A and B, is very 50-50. Like let's say you got 2, right? They will be approximately 1 and 1 when you do it this way. Not 100%, but you will see here. So let's say you try to balance this. So C you cannot balance. You can balance. So you balance O. You can balance. So yeah, now you can see here. Because when you balance O, right, then you have A and B. So 2 equations, they will just give you 1 and 1. It's very likely to be this case if you assume this answer. So that's why I said I don't really fancy this assumption much. But this is what we do if the question doesn't give you the output. Okay, so then yeah, the next slide is still just the dry and wet analysis. So it's same thing. Different also not lah, but that's what I'm saying, slightly different. You can also get easy. Okay. So example 4, we carry forward the question from example 3. The stoichiometric mixture. You are asked to calculate the volume of the mixture per kilogram of fuel at a temperature of 65 degrees Celsius and a pressure of 101.3 kilopascal. And number 2, the volume of the products of the combustion per kilogram of fuel after cooling to a temperature of 120 degrees Celsius and a pressure of 100 kilopascal. Yes. It's really equal to MRT, but how?
First one is just PV MRT
Of what?
of the field.
M your R, your N, your R. What do you use?
We need to find
So this is where you can see chapter 3 and 4 we combine a little bit just to see how it works. So these two chapters usually I put them together one, I don't ask them separately. PV equals to MRT is not wrong, but how?
NR just using the NR.
Then what will your N be?
N is the
Mole.
stoichiometry, because the stoichiometry is 9.
That one is air fuel mixture. Okay, so now this question by theory is not hard. The issue will be understanding what the question wants. So we look at 1, okay? So 1 asks for the volume of the mixture. This is your focus. So for every kilogram of the fuel. So what is the mixture? The mixture will actually be your entire reactant. That will be your mixture. So your fuel, every mixture of oil, correct? So that's it. So we carry this equation over. This one we know the value is 3 lah. This one, right? So let's say I think when I solved this one I was a bit stupid lah. So it was long time ago when I tried to solve this because this example, some of them the answer is given last time, the old book. This is from a very old book. So let's see. If we assume 1 kilomole of fuel, maybe this is easier, maybe this is harder, I don't know. So let's say if we assume 1 kilomole of fuel, it will mean that the mass of the fuel is 46 kg. Because we have C2, H6 and O. And the total number of mole of the mixture would be 1 plus 4.76 times 3. Make sense? This is the number of mole of the mixture. So this entire thing is mixture. So then you look for the volume of the mixture. So this will be the volume of the mixture. So we use the mole version so that we don't need to purposely find the mixture molar mass or something. So P is 101.3, then T is that temperature given to you. 15.28 is this kilomole, then 8.314 for IU. So then volume of the mixture per kilogram of the fuel, you just use that value divided by 46. So if you feel like it, you can also do the other way around. You assume 1 kg of fuel, then you find the mole here, but then the one I feel maybe longer. But then when you divide, then you don't need to divide, you can just 1 kg. So either way, so here we assume 1 kilomole. So again, if you assume 1 kilogram of fuel, then you need to find this mole. Then you need to balance again. Then same thing, the rest are opposite. Volume of the mixture, we ask for the volume of the products. So the product will be everything on the right hand side of the equation. So once again it's 3. So everything on the right hand side of the equation. So same thing here, fuel is 46 kg. So on the right hand side you have 2 plus 3 plus 11.28. We have a total of 16.28 kilomole. So remember, mole is never constant. Whatever that is constant is mass. So from here, do the same thing, then we find the volume of the product per kilogram of fuel. next week we can enter the tutorial. Okay, so now something a bit different, so that it's not so boring. So a gas engine is supplied with natural gas of the following composition. So this is by this gas, so by volume. If the air-fuel ratio is 30 by volume, so this is the actual. So this question, what we are given is this is the actual air-fuel ratio, okay? Calculate the analysis of the dry products of the combustion. It can be assumed that the stoichiometric air-fuel ratio is less than 30. So what are we trying to say here? What is the question trying to say? Yes. We have excess A here. Because this is your actual, so your actual is 30. The stoichiometric one is less than 30. So it means you have excess A. Which also means that you act, so this is one of those rare questions where you can actually solve the question without finding the stoichiometric. Well, in fact, for this question, actually it's pointless to find the stoichiometric because you are not given in terms of percentage. You are actually given the actual amount of air directly. So what you can do here is actually very simple. What do you do? So we know that stoichiometric air-fuel ratio is less than 30, so meaning we have excess air. So what can we do with this 30? 30 is ideal. No, 30 is actual. Stoichiometric is ideal. 30 is the actual one. So the current case you have 30 air-fuel ratio. And we are telling you that this 30 is more than the stoichiometric. So which means that's why you have excess air. So how can you make use of the stoichiometric? No. So that's why I said just now, for this question, you don't need stoichiometric. This is one of the rare questions. Most questions you will need. Because most of the other questions, let's say I tell you 20% excess. But how much is that going to be? You don't know one. So you have to find the stoichiometric. But in this case, you are given the actual air-fuel ratio. So you don't actually need the stoichiometric. No, stoichiometric is less than 30, but you don't know how much excess also. That's why I say the stoichiometric is useless. So what do you know here? So we know that actual air by volume, okay, is 30. So meaning this is 30 kilomole of air over 1 kilomole of fuel. Right? So let's say we do our usual. We assume that this question we have 1 kilomole of total fuel. Okay? So which means the total number of air you can find by using 30 divided by 4.76. So we are going the other way around, essentially. So then when you write this equation, so this whole thing, your fuel is 1 kilomole, then your air, you will have 6.303. Usually it's the other way around. We use 6.0303 multiplied by 4.76, you get 30. So now we do it the other way around. And since we know that this is an excess air case, then your product will be CO2, H2O, O2, then N2. Make sense? Then you balance them.
Can I see a previous slide? Previous slide.
Semester is the question.
See again.
You don't have it?
You will write something on the slide.
Oh, yeah.
You wrote something.
You want nothing significant, I'm just saying that one is actual. Alright, so so this question we give it a little bit of twist, but you can see actually two same steps up. Tutorial we will have, I remember at least one question that is quite complicated. That one more we have to discuss. The rest I remember not too different lah. We'll see. Okay? Okay, so then last slide, we just give you the answer for the, so just like usual, I give you the answer for the analysis. Okay, so I will stop here, but I still have two things that I want to talk to you about. Okay, one thing is definitely your test all, yeah. So the test will be until this chapter, so
Until this chapter.
not going to be next week. So 2 weeks later. Okay, Tuesday.
Until this chapter or until this chapter?
We can, no? So we can. Okay?
Until this chapter, not under.
We only 4 chapters and so far. Last slide. Okay, so yeah, with that.